think we can start now. So hello everyone, and thanks for being here, and welcome to the first and the kickoff or the launch virtual meetup for PyData Helsinki. We are super happy and excited to have you here for this first event from the PyData Helsinki initiative. And we are really super excited about this series of meetup that we will be organizing here in Helsinki, bringing you the best of guests doing amazing stuff with data and Python. And for today, for the kickoff virtual meetup, we have two amazing speakers with two interesting talks. We have Oguzhan and Deniz. They will be talking about data augmentation and explaining machine learning models. So for today's agenda, it's a bit simple. So we'll start with an introduction, introduce PyData Helsinki and what is PyData initiative. And then we will tackle both talks. We will start with the best practices for data augmentation, and after take some questions and answers. And after that, go with the second talk, where Deniz will walk us through explaining machine learning models in 2020. And after that, we can take again some questions and answers. And finally, we'll close with some closing words and overall discussion and chatting. All right, so what is PyData Helsinki, or who we are? So PyData Helsinki is the local meetup chapter for the PyData initiative, so which is a worldwide community of users, developers, and enthusiasts working on data analysis tools, and they are gathering together to share ideas and learn from each other. So the idea behind PyData Helsinki is to have this kind of monthly meetups in a fixed day that we will announce later. So the idea is to bring you some speakers who can share their knowledge and expertise in the field of data and Python in general. Those meetups will be organized by mainly 3 volunteers for now. There is Ali Iladi, Hunain Dirar, and me, Tali Butagard. I'm not sure if I turned on my camera or not. All right. Okay, cool. Yeah, so as I said, we are currently 2 volunteers organizing those monthly meetups, but we are currently also looking for additional organizers who can help us with the organization. So please, if you are interested in helping us organizing those monthly meetups, please feel free to reach out to us or to reach out to one of the volunteers or email us at pydatahelsinki@gmail.com. So what is PyData? So I will give you a quick introduction about PyData and what is the organization behind it. So PyData is an educational program of the organization NonFocus, which is a non-profit organization working on a lot of open source data projects. And it's a community driven by conferences and meetups, and we welcome all the beginners and novice to advanced and expert people in the field. And we are here to share our ideas about data analysis tool, machine learning, best practices, and all the cool stuff. So as I mentioned, PyData is a program provided by the NonFocus organization, which is the home of the open source projects in the scientific Python data stack. And NonFocus actually supports both users and contributors for those open source projects. And as we can see here from the picture, NonFocus is backing a lot of interesting open source tools that we use in our daily data science job. For example, Pandas, Jupyter Notebook, Julia, Dask, SciPy, etc. And if you want to learn more about NonFocus, please feel free to visit the official NonFocus website. All right, so where is PyData in 2020? So currently, PyData meetups or chapters are happening in 63 countries in about 180 cities. And the community is about 173,000 members, which is quite huge. And recently, we are super excited about launching the Helsinki chapter, which was really missing. All right, so how can you get involved? So first of all, we welcome all of you to participate on those local meetups. Currently, we are doing it in a virtual way due to the current circumstances, but hopefully in the future, we will have in-person and physical meetups. So please participate in those meetups and please come to speak. So if you are interested in delivering talks, please feel free to reach out to us. We are here to help you to share your ideas and learn from each other about the best practices, new approaches, and emerging technologies related to data and Python in general. And also, you can get involved by attending our local PyData meetups or participating in the worldwide conferences organized by PyData organization. And of course, you can also donate or work with your company to sponsor our PyData local meetup or sponsor PyData general conferences or global conferences. Okay, so we have an announcement here. So in the next couple of days, there will be a huge PyData global event, which is probably the biggest online data science conference of the year. So it's 5 days packed with talks, tutorials, posters, open source, sprints. So a lot of good stuff. So please, if you are interested in joining the PyData Global, visit the website global.pydata.org to get your ticket. And you can pay whatever you want for the ticket, just as a contribution for PyData. All right, so this meetup or the upcoming meetups, they will be organized and governed by this code of conduct. So please be kind to each other, do not insult or put down others, behave professionally, and remember that harassment and sexist or racist or exclusionary jokes and language are not appropriate for PyData. So this is the PyData Code of Conduct. And if you want to read more about it, please visit PyData official website. All right, so if you have any questions or comments or recommendations, please email us at pydatahelsinki.com, pydatahelsinki@gmail.com. We are also available on Twitter at PyDataHelsinki, or you can reach out to one of us, one of the organizers directly. And I want to mention also that we are currently looking for speakers for the upcoming months. So please, if you are interested, feel free to reach out. And we are also looking for sponsors for the upcoming online meetups and hopefully the upcoming physical meetups. All right, so let's get into it with the first talk of today. So we have Oguzhan Gencoglu, who is the co-founder and head of AI at Top Data Science, and he will be talking about best practices for data augmentation. So, Oguzhan, the stage is yours. You can.
Hello, everybody.
Yeah.
First of all, thank you for your time in advance. It's a pleasure to be here and to open the first PyData Helsinki conference and meetup. I would quickly share my screen. All right. So my name is Oguzhan Gencoglu. I'm co-founder and head of AI at Top Data Science, leading about 20 data scientists at Top Data Science. We are a Helsinki-based AI consultancy, and we solve our clients' problems with machine learning. And today I'll be talking about best practices of data augmentation. I will be talking about, of course, first what data augmentation is, if you are not familiar with that, and I'll be giving several examples of data augmentation in various domains, such as computer vision, natural language processing, etc. So my outline will be as such. First, I'll introduce data augmentation and the scientific rationale behind it. I'll give a couple of remarks that is kind of generic to whatever data augmentation you are performing. And I will right away dive into best practices. I'll give examples from computer vision, what is the state of the art, what you should actually be aware of, what you should be careful of. Similarly, in NLP, I will be mentioning a couple of cool tricks in that domain, and some examples and libraries in a couple of other, let's say, modalities such as time series or tabular data. And then I will give a couple of a bit more advanced maybe use cases of data augmentation in research as well as in the industry. So I play factual, meaning that I try to give references, scientific references when I claim something. So if you see this green box somewhere down any slide, it means that is the reference publication you can go further, have a read on. And if you see a red box, it means it's a library. For this meetup, I focused only on Python. So in red boxes, I will give the Python library that you can apply those things told in that slide. So this is kind of the structure of my slides. Okay, so let's right away dive into data augmentation. Meanwhile, you can write your questions or comments in the chat part, because we will have a question and answering session so that you don't forget. So data augmentation is basically increasing your training data size by diversifying your data. I would like you to focus on the diversifying your data, training data, more than increasing the training size part. I will elaborate a bit more on that, but basically, if you have run any kind of data science or machine learning projects, every company has at least one person, whatever you present, saying that just collect more data. And this is where I believe data augmentation originated from, because we data scientists, we would like to get the work done without actually doing too much hassle. So we want to get the job done without doing the work. So we, of course, obviously thought that how can we simulate sampling from real data distributions? So sampling from nature, meaning collecting data programmatically in a synthetic way, partly automatically. So data augmentation means that basically introducing some noise, some perturbations, small changes to your training data so that you increase the diversity of your data, which helps in several aspects. So the scientific rationale is this talk is a bit focused on neural networks and deep learning, but many of the things are also generic. But from a neural networks perspective, neural networks are universal function approximators, universal approximation theorem, meaning that you can basically fit any function perfectly, meaning that you can actually achieve zero training or error with even single layer neural network. You don't need a deep neural network, which is quite bad because we don't want zero training error. It doesn't mean that we will generalize. So these kind of methods and algorithms, machine learning models, are very easy to overfit. And by diversifying your data, by increasing your training data size, you make the model, you give a hard time to the model to overfit. So actually, it serves as a regularization purpose, actually. And a bit, I'm not going into details, but the choice of data augmentation should, in general, be taken care of depending on your neural network architecture. For example, let's say convolutional neural networks, they are translation equivariant, meaning that an object on the left of the image shouldn't matter if it's on the right or left. So if you translate an object in the image, the convolutional neural networks should be able to learn representation of those. So maybe translation augmentation is not actually, it's a bit redundant made before convolutional neural nets, these kind of things. And typically state-of-the-art results are achieved in research with data augmentation. So it's been a really common practice, actually, both during time as well as during inference time, which we call test time augmentation, which I have a slide about. So a couple of remarks. The focus, as I said, should be diversifying the data, and it's not a new concept in a sense that it's pretty much rooted in sampling theory, because you are trying to sample from a distribution, hopefully resembling actual data distribution in nature. And this is very important. Your data augmentations optimally should be domain and task dependent. They are, and you should make use of that. So domain expertise when you are coming up with specific custom data augmentations is crucial. I will give examples about that. So if everything's all right, I would right away dive into best practices. First, I will talk about best practices of generic data augmentation. These things apply to computer vision, tabular data, natural language processing like text data, etc. Then I will further on down into that kind of modality-specific augmentations. So the first thing I would like to recommend is use the domain knowledge when you select your augmentations or implement a custom augmentation. So domain knowledge means the task at hand usually, almost always, have certain kind of prior information or prior knowledge that's available to you or to the domain experts. And it's quite important to make use of that domain knowledge when you devise basically your data augmentations. For example, let's say you are building an object detection model or an image classification model, etc., and you want to put this into production where there's a camera, but the camera stream, you know that the camera stream is giving you, let's say, JPEG images. JPEG is a lossy compression, so it actually decreases the quality of the image. But your training data is all nice, high quality images. So what you should do is that using that knowledge that, hey, this camera, the security camera or whatever, is kind of low quality and it's doing this compression, I should augment my training data during training time with JPEG compression. It's an augmentation technique so that the training data, statistical distribution of the training data resembles the statistical distribution of the data in production or test data, if you want to call that. Second example, let's say you are doing a text classification. You have this text, glycerol is a whatever. I just copied this from Wikipedia actually, and the label is biology. This text is about biology or chemistry. It can be, and as a chemist or as a biologist, you also know that glycerol has another name, glycerine or glycerine, and you would like to add these kind of versions of your data as data augmentation, so that you use the domain knowledge and increase the diversity of your training data. This was an example from natural language processing. Second best practice, please augment only the training data. So we have training, validation, and holdout data, so test data if you call it. We don't wanna augment the validation data. So we augment the training data only. This is I hope this makes sense to you. This is quite important to have fair comparisons and realistic estimation of errors actually when you put things into production. All right, continuing. So randomness is your friend, especially when you are training neural networks. We like randomness or stochasticity, right? So neural network training is a non-convex optimization problem. I will not go into details of this. Meaning that it's NP hard, meaning that you are not really actually searching for global minimum, because finding it is pretty damn difficult. So you are okay with local minima, and the problem is you get stuck there in local minima or in saddle points, and there are several like there's plethora of research that shows that when you do, for example, this batch gradient descent, so randomly select certain batch of data. You don't like always give the same sequence of data. You randomize things. It eases for you to generalize more. You can move from this kind of saddle points or local minima easier. So this is from a data augmentation perspective. It helps your training and generalization power when you add more randomness. So make things more random. Which comes to the practice of it. So please do not augment your data and save it to your computer or to a database or hard drive and then train a model. Because even though you can introduce this augmentation with a probabilistic way so that it's random, it's also like a kind of fixed once you create those actually augmented data. And also you actually use lots of storage space, etc. What we typically do is we augment on the fly while training a model. So this is quite a good practice to have. So on the fly, you randomly some part of the data is like transformed, perturbed, whatever your augmentations is. Some part of the observations, some of the observations are augmented with certain probability, with certain augmentations. So this kind of randomness on the fly, that's a good practice. It's important to profile your training. So typically data augmentations happens on CPU. And neural networks you train neural networks in GPU. So usually you shouldn't have speed bottlenecks because of augmentations, because usually the heavy part of training a model is happening on the GPU, and flipping images or stuff like that shouldn't slow down your training. But if you have a custom augmentation, something very computationally heavy, for whatever reason you implemented this, it's important for your domain, let's say, it may slow down actually your training. So also realize that some augmentations can be actually done on GPU, and I believe this is kind of the path where we are heading actually in the industry and in the research. So profiling the speed of your training, turning on and off the augmentations to see if it makes sense, it's a good practice. Now, I get lots of questions that, okay, which data augmentations to choose and their probabilities, aren't they hyperparameters? Technically, yes. So which type of data augmentation? It's a categorical hyperparameter. If you can choose from 10, like you can turn on and off each, so you have 10 hyperparameters. Then each augmentation, let's say the strength of rotation or how much you want to rotate the angle, that's a parameter of the kind of augmentation itself. Then if you want to assign separate different probabilities to each augmentation, so this thing explodes, right? So you don't want to do some hyperparameter optimization on every single, this probability of this augmentation should be optimal. We don't have that much time and computation power. So kind of simplify things, right? So group maybe type of augmentations, for example, from image or computer vision, rotation, shifting, affine transform or scaling. Group them into geometric transformation category maybe, so they are happening together. Set the probability of each augmentation to a single value. Maybe you don't want to have 0.2 for this, 0.35 for this, so it really explodes your search space. So keep it simple. Play with the probability of you want to augment this sample with or not. Play with that kind of strength of augmentation. This is kind of a way to simplify this whole data augmentation parameter tuning, if you want to call it. And finally, always visualize. This is like one of the most important things. Before training, always visualize, inspect manually. Does these augmentations make sense? Look at your images, augmented images, look at your augmented text, videos, etc. because you don't want to mess up your training. They should make sense. This is quite important. All right, let's dive into computer vision. So very typical augmentations is changing the shuffling the color space, affine transform, or this kind of inverting the actually color space. You can play with exposure, so lighting of the image. You can rotate, and you can change the alpha channel, etc. These are pretty typical augmentations. You can add some noise, salt and pepper noise, or other kinds of blur, motion blur. You can add some domain-specific augmentations as well. Something or JPEG compression, this kind of compression augmentations. Something I really would like to recommend is this Augmentations library. I use it quite a lot with my team. Of course, TensorFlow, PyTorch, other libraries have all their internal, let's say, data augmentation, let's say, functionalities. But Augmentations is a well-documented, well-growing library that has many different augmentations, image augmentations in it. So feel free to check it out. The current state of the art in computer vision, kind of peer-reviewed and published, is mix-up, cutout, and cut-mix augmentations. So in mix-up, you actually would like to mix several for image classification, right? Several classes together, like you have your cat and the dog together. Cutout, you actually simply cut out a huge portion of the image, and cut mix is actually you put an image from, or a portion from another class into it. So feel free to also check these if you want to try these out. Now I would like to emphasize, if you have volumetric data, so 3D data, for example, medical images like MR, CT, it's kind of slices of 2D images, meaning that you have a 3D structure. You should be careful when you are augmenting each slice. Actually, you shouldn't do that, because one slice here is augmented with this augmentation, and the second slice is perturbed with another augmentation. You kind of lose the whole 3D structure, right? So instead, use Torch.io. I don't know if it's pronounced like that, a library, which actually, if you watch carefully, this is a movie, like in this slide, you can actually modify the whole data in a 3D manner without losing the 3D shape. So this is a cool library. And similarly for video, you wanna apply data augmentation to each frame, the same augmentation to each frame of a video, so that you don't lose the logic there. Let's talk about NLP. So you can have character level augmentations. So you can, for example, insert some characters, delete some characters, or simulate keyboard errors, so typing error. You can have word level augmentations. You can substitute some synonyms. This is pretty common. You can use another actually pre-trained model to insert some contextual words, something like bird, for example. You can swap or delete words, or you can have sentence level augmentations. You can insert sentences using a GPT-2 kind of models. You can shuffle sentences. You can create this kind of diversity. You can increase your training data size with these kind of tricks. And NLP Aug is the library I used a couple of times. It's quite nice for NLP augmentations. An example here, for example, if the original sentence is a sad, superior human comedy played out on the back roads of life, you can change sad with a synonym, lamentable. You can randomly insert some words, swap some words, or delete some words. Just an illustration of how these things work. All right, so Another trick in NLP is back translation. So you can translate your English into, for example, French, and back translate to English. This gives some kind of variation, which is used nowadays quite a lot. And for time series, tabular and audio data, there are several libraries: DeltaPy, CTGAN. These are for tabular data. For example, CTGAN trains a generative model, generative adversarial network out of your tabular data, and then you can sample actually from that distribution to augment tabular data. Augmentations, you can use it to augment audio data. And I have a couple of slides left, only a couple of other use cases. Test time augmentation, if you see in a paper TTA, it means test time augmentation, meaning that during inference, during prediction time, you can actually boost your model performance. For example, you can pass through your model, you can predict several versions of the images, augmented versions of your image or your text, and get your predictions and do some ensemble. Maybe you can do majority voting, or pick the one that is most confident, or do some averaging of the probabilities, etc. So this usually, test time augmentation usually boosts up your, let's say, model performance a couple of percent. So if you want to squeeze the most out of everything, go ahead and apply. Obviously, there's no free lunch, so the downside is that you need to predict all those three, for example, augmentations, meaning that you need to run predictions 3 times, so your results will be, you need to wait 3 times more, so it will be slower. Then some recent papers actually published turned this into a meta-learning problem. So trying to learn what is the best augmentation for a given task. So using, for example, reinforcement learning, this is a bit falling into AutoML, automated machine learning, like craze. So for example, this paper, the last paper in the references, it actually learns with reinforcement learning, like the best combination of augmentations for that specific task. So you can do, if you have enough computation power, you don't even have to define those augmentation combinations, but you can actually make the neural network learn, or the model learn those things. And some interesting ideas is that we augment always in the raw data, original data space, but you can actually augment on the latent space, meaning that on the representation space. So this is an interesting idea, that you can extrapolate, interpolate, add some noise on the learned representation space, like feature space, and augment the data there. This is an interesting idea. And finally, AI models propagate or even reinforce social biases. For example, pick any language model. Actually, it's a couple of lines of code, and you can perform this masked word prediction. So just mask a word and make the model predict that word. And if you, for example, have such a sentence, if you predict what is the probabilities of words coming instead of the mask, and he is an engineer with the probability 79, and it has much less probability, you will see there are hundreds of papers written about this bias in AI models, and other words have maybe even lower probabilities. But this is obviously kind of a bias, a social bias kind of injected into the AI model. And you can use data augmentation, so you can replace he's and she's, so you can make things more fair, more balanced in your training data to kind of counteract this bias in AI models. So that was it from me. I hope you enjoyed it. I hope you learned something. It was my pleasure, and I would be happy to answer your questions as much as I can. Thank you very much.
All right. Thank you so much, Oguzhan. That was really interesting. Yeah, actually, we have a couple of questions in the chat. I can read some of them. So yeah. First question from Oki Kiola. He or she asked about, where is the data stored and what format is it stored in? Is it variably the same size as the actual image?
Yeah, actually, as I mentioned, we don't want to store the augmented data. So you have your data, it's stored somewhere, wherever your system is in your computer, in a database. We want to apply augmentations like perturbations, changes on the fly during the neural network training. So we don't save those actually. So during the model training, we would like to apply those changes, and the model learns from those. So typically we don't wanna save those augmentations.
All right, I guess that's clear. So another question from Xenia. He or she asked about when we are talking about state-of-the-art in data augmentation, what exactly does it mean?
It's a bit kind of the how machine learning research is done. I don't want to go into that discussion, but we have well-known, let's say, data sets, for example, COCO, ImageNet, etc. For image classification, object detection, image segmentation, semantic segmentation, all these computer vision tasks. And typically state-of-the-art means that having everything else equal, meaning the same neural network architecture, same training parameters, learning rate, etc., they change the augmentation type and test which one performs better. So that's what I meant. Those new augmentations I introduced were the ones that performed the better than others. So one comment can be is this a fair comparison? Because when you change the data augmentation and maybe even the probabilities, the neural network parameters, you should change maybe the learning rate, etc. So I'm just like kind of stating what has been used. If you want to choose a couple of good augmentations, it was mix-up, cut mix, and similar augmentations currently used.
All right, thanks. So Maria is asking, when dealing with smaller language groups like Finnish, Swedish, how would you augment content with NLP?
So some of the NLP augmentations I mentioned, they can be applied to any language, meaning that you can swap images, you can swap words, characters, delete them, you can swap sentences, insert characters. But for Finnish language specific, for example, you can use a word stemmer, Finnish word stemmer, and change the suffix, because Finnish is such a language that you have lots of versions of a noun, like koulu, koulussa, koulusta, etc. So you can play with that by just stemming those words, or you can use for example, multilingual language model such as multilingual BERT to insert some words that actually make sense when you read the sentences, like contextualized word representations. Or you can use actually a language model trained on Finnish language. For example, I think Turku University or Åbo Academy has a Finnish BERT. So you can use even Finnish specific insertions or deletion in like this kind of contextual word or language sentence insertions. That's what I would do. And you can always do back translation, translate to English and back to Finnish. I don't know if there's any machine translation model for that though.
Yeah. All right. So another question from Tommaso. He's asking, how much data augmentation is too much? Especially in the NLP, I imagine that too much augmentation would eventually distort the meaning of the sentence.
That's correct. That's for sure. There's such a point that you actually distort the image so much that it's completely from a different sampled from a different statistical distribution. In computer vision or NLP, that's a fact. So I don't have an answer because that's a domain specific, so problem specific thing. But the cool thing I introduced is that you keep the probabilities of each augmentations fixed, and just play with if you just play with the probability, this one hyperparameter, do you augment this sample or not, and just sweep it a bit, like play around with that a bit, you will see more or less a cutoff point that it's too much. So do not over-engineer that play with each probability of each augmentation, because then that's like a huge thing computation wise. So with couple of trainings you will actually have a more or less a cut point that, okay, this much of probability is okay for data augmentation.
All right. We have another question in the context of evaluating the data augmentation. So Carita is asking if there is some sort of metrics that could be used as a guideline to evaluate the quality of data augmentation.
Typically, we would like to evaluate our whatever we do in our choice of architecture, choice of parameters, like our design, choice of algorithm. We will evaluate all that using a validation set, right? Validation data. So this is the same. It's better if you cross-validate things, sure. So basically, it's the same. That's why you don't touch the validation data. You don't augment it. You keep the same validation data and try out different augmentations, or use augmentation or not to compare that. Now, there's one recent paper that actually, it's a bit advanced, but they actually try to find such a subset of data that if you try the augmentations on that, it will generalize the performance of that augmentations, like this is better or this is better. That knowledge will generalize to the whole data set. So you can run lots of trainings because it's a small subset of data, but they turn that into a learning problem itself. You might want to check that out.
All right. Okay, so I guess the last question would be, so it's from Andrea, and it looks like data augmentation might also be used to add a bias within the data. Is it possible in your opinion?
Yeah, that's possible. You should be careful about that.
Yeah.
The thing about bias or fairness, this fairness concept. So there are several fairness metrics that we can use to basically evaluate how fair two models are. And the bummer is that it's mathematically impossible to actually comply with all those fairness, let's say, metrics or constraints simultaneously. So it's kind of a Pareto thing that if you make your model fair in some sense, it becomes unfair, more unfair in another sense. If you can email me, I can send you the paper that proves that actually.
All right, sounds good. Yeah, I think we can take one last question. So Maxim is asking if you have any thoughts on pseudo-labeling techniques.
That is quite relevant with the current research. Also, thanks for asking that. I didn't want to go into that because there's no time. So this whole pseudo-labeling or self-supervision, it's quite important with the data augmentation, simply because I don't have time to go explain what self-supervised, let's say, pre-training is, but so for people who don't know that, instead of annotating a lot of data, you want to use a weaker model basically to pseudo-label. So you predict the labels of your unannotated data and train with those labels. So you constantly, iteratively increase the training size actually, and a couple of errors there and there, it's okay. So this is the logic there, and this is pseudo-labeling. I haven't used pseudo-labeling and data augmentation in an industrial project that is actually in production, but it's something I would like to actually also experiment with, because I would definitely use data augmentation in there.
All right, sounds great. Thank you so much, Oguzhan. That was really
Thank you very much.
And if anyone is interested in reaching out to you, where they can find you?
They can add me on LinkedIn. They can find my email, my name.surname @topdatascience.com.
All right, sounds great. Thank you so much.
Thanks.
All right. So before moving to the next or the second talk, I will quickly plug this announcement here. So as I mentioned in the introduction, the PyData Global Worldwide Conference is coming up, and it's taking place in the 11th to the 5th of this November. So it's a 5 days conference, online conference, fully packed with talks, tutorials, and posters. So please, if you are interested in joining the PyData Global, head to the global.pydata.org and get your tickets. So you can actually pay whatever you want, just as a contribution for the PyData community. All right, so let's move on to the second talk. So it's going to be delivered by Denis Vorotinitsev. He's a senior data scientist at Aura, the Finnish startup, and he will be talking about explaining machine learning models in 2020. Denis, the stage is yours.
Yeah, thanks. Yeah, now you should be able to see my screen. So yeah, first of all, thank you for coming. I'm really excited to be here and present this material to you. My name is Denis, and today I'd like to share, today I'd like to share some thoughts on how to interpret machine learning models with a modern Python tools. So recently I worked a lot with interpretation machine learning, and I have some experience which I'd like to share. Let's start. Yep. Yeah, so I'm working as senior data scientist at Aura. We are making rings for well-being which are capable for tracking your sleep. And we're using this data in order to improve person's sleep and overall well-being. Our most famous and recent project to which I was involved is early COVID detection based on the data collected from a ring. Before that, I was working at VTT Research Center of Finland, where I was helping to detect anomalies during steel manufacturing using machine learning. I'd like to start my presentation by asking a question. Why do we actually need explainable machine learning? How it can help data scientists to achieve his or her goals, and how it could help a company? Personally, I ask these questions the following way. So imagine we want to solve some business problem, and when we're solving business problem, our main goal is actually optimize profit or some other metric given a set of constraints. So we have some data, we're creating target that we want to predict, and then we will use this target in our business process. Unfortunately, machine learning models cannot optimize profits as is, so we create this proxy metric. It can be, for example, binary accuracy or log loss or anything else. And to optimizing this proxy metric, we claim that the model, the pipeline, which achieved the highest score on the holdout data set, probably is the best model, and we should use this model in our production settings. And now the interesting part begins. When we're collecting data, our collected data is not actually the real world. It's just a representation of the world. It's words mapping. And by collecting some data, we're inducing selection bias by default. By training our model only on subset data of all available data, we're also inducing other sorts of biases. We may create a bug in our pipelines. Models are also just a mapping of the data, and so on and so forth. So at the end, we may end up in the situation where our final metrics, our final proxy metrics, such as accuracy might be pretty good on the holdout and test data sets. But in reality, our solutions are suboptimal. So they're optimal for our proxy metrics, but they're not optimal for our metric which we want to maximize, which is profit or any other utility metric that we want to use. And for me, the possible way to solve this problem is to actually start interpreting our models, start to understand what is going on under the hood in this black box of the model. And for me, this interpretation is just a final stage before pushing models to production, is to test our model. Is it actually delivering what we're expected it to deliver, or it just overfitted towards some artifacts in our data set or biases in the data set? And this problem of bias is actually really important nowadays. If we go to Google and Google AI biases, we will find a lot of articles related to the topic. And the society, the people are really interested to understand that the models which were created as data scientists are actually not using these biases, that they're not biased in any sense. And also, this topic of interpretation of machine learning models is quite popular in the papers in the scientific world nowadays. So since 2010, we see an exponential growth in the number of papers on the interpretation machine learning, which is pretty nice. But personally, I feel this gap between what researchers can show us, can write about, and the actual data scientists who are creating these models and pushing them into production. And for me, the place of interpretation machine learning is something between evaluation stage of the ML pipeline and deployment stage of the machine learning pipeline. And I talked with a number of data scientists. We discussed how they approach interpreting machine learning models, what decisions they made after interpretation, and so on. And I had this feeling that in reality, interpretation is just not very useful stage of ML pipeline. You just calculate sharp importance for every feature in your data set. You show, let's say, top 5 most important features to your stakeholders. They replied, well, that looks good to me. Let's push it into production. Or even they don't say that, it's fine. So it's probably model knows best. This idea is actually taken from the paper called Interpretability, in which authors asked data scientists what decision they are making based on the interpretation, and it turned out that no matter what interpretations will be shown to the data scientists, they are willing to push machine learning to production no matter what. So to check if it's really a problem, because obviously it is a problem, but is it actually a real problem, or just I talked with a data scientists who are not very into this field? I decided to ask the following questionnaire in the 2 communities. First one is MLOps community, second one Open Data Science, 2 very famous data science related communities. And the questionnaire was following. So select which describes you or your company best. 3 options. First one, we don't interpret our models or do it occasionally. Second option, interpretation is a part of our pipeline, but we only calculate sharp importance. And the third one is that interpretation is a part of our data science pipeline, and we use several models such as SHAP, LIME, GAM, PDP, and et cetera. And it turned out that just 6% of data scientists in open data science out of about 100 participants, they answered that they actually use something besides SHAP. The vast majority of data scientists are not actually using any tools or just calculating SHAP. So the problem which I described on the previous slide. And I believe it is a problem. Why it is a problem? Because SHAP is a great tool, no doubts here. It's probably state of the art for finding most important features for your model. But it cannot, by design, answer other questions, such as what are the most important training points in your data, or what is dependency between feature and prediction globally according to the model, and all other questions which are listed on the screen. And these questions, they're actually really important, because when you're trying to interpret your model, you try to understand how it's making decision. You cannot only use most important features, because it's not the only question you should ask. You should ask several questions. And that's why I'm actually proposing to use the framework which I'm currently using myself. So it's pretty simple. It's not perfect, obviously, but it's okay for me, at least. It consists of 4 main questions, which I ask during interpretation. And after answering each of those questions, I make a decision, should I rework this model or continue to the next stage of interpretation. Let's go through each question step by step. So the first one is following. Do we have the same metrics across different subgroups? And here subgroups could mean like anything. It could be subgroups based on some cohorts of users, such as gender, race, age. We want our model to perform well enough on all of those groups, because in our production settings we are expecting to see all of those users. Also, subgroups could be some clusters in the data which are not related by user race, for example, or gender, but related to something else, maybe number of purchase or something else. And so the question that we want to answer again is that we want to see the same metrics across different subgroups. If we are not seeing same metrics across different subgroups, it might be a signal that you have a bias in your data, and you try to find those biases and remove it. Or it might be, again, an artifact of the data set. For example, the subgroups can be different, and that's why model just find these differences between those subgroups, and the final results are because of those differences. In that case, if it's normal, if it's not because a bias in the data set, you may just create different models for those different subgroups. And commonly, the performance of several models trained on different subgroups is better than just one model which fits them all. Personally, I use my own custom script, which just generates a report for predefined set of groups of users, and I just check the scores manually. But I really like this idea, which was presented by guys from Uber, the library called Manifold. The idea is following. So we train our model. We are making predictions for our holdout data set, and then we cluster our data based on the difference between actual prediction and and actual label. So on the right part of the screen here, you see upper image. You see 3 clusters, 3 segments. The x-axis is log loss, and we see that for segment number 0, the log loss is low, which means that for this subgroup of users, model performs extremely good. For segment 1 and segment 2, log loss is higher, and we may check why model made a mistake in those subgroups. And we may again use Manifold here. We say that segment 0 is group 1, segment 1 and segment 2 is group 0, and we compare different features based on those different clusters. And we may see that, for example, bottom picture, feature number 0 has a different distributions across 2 different segments. And it might give us insights on what should be changed in our processing, or it might tell us that, hey, maybe it's worth adding a new model and train 2 separate models for these 2 separate segments of users. The next part, the next question to ask is, what are the most important features of the model? And here we are checking if the most important features are actually expected. So what I do, before looking into most important features, I just write down list of expected features, and then compare it to the features which are achieved by SHAP or any other tool. Why I'm doing that? Because if I'm not doing that, there is a risk, there is a chance of me doing hypothesis after results are known. It's not a good bias, and that's why I'm trying to avoid this, making hypotheses after seeing results. Because again, in some cases, you might just say, hey, well, it's unexpected, but it still looks good to me, so let's move on. And I want to avoid that. So here, this is pretty straightforward. The state of the art is SHAP. I recommend to use it for finding most important features. If you're training tree-based models such as LightGBM, XGBoost, pay attention to the gain importance of your models. Also, you may find very interesting library called Dalex. This library could provide you the pretty pictures. One of them are presented on the bottom part of the slide, right part of the slide. So this library is actually calculating very same output as SHAP, but it is presented in a better way. In SHAP, the output for each local interpretation is just log it. In Dalex, it's converted to probabilities, and I find this plot more beautiful than one in the one is generated in SHAP. And also, I know that some data scientists are using Lime for both global and local interpretation. Sometimes I don't recommend to do that because Lime has a lot of problems, like three, but very huge problems. First one is that the fidelity of Lime interpretation is really low. Fidelity is an accuracy of your surrogate model, in our case, in the case of Lime. So the accuracy of surrogate model is not high enough, and that means that interpretation is not also very accurate. And the second problem of Lime is that interpretation are actually based on the choice of hyperparameters. So depending on what hyperparameters you are going to choose in Lime, you may end up in the situation where you have just contradictory interpretations, which is not a desirable property of interpretation tool. And the third problem is that interpretation depends on the input a lot. So if you change input even slightly, you may have a different interpretation. So interpretations are not robust towards small distortions in the input. Many interpretation tools have this problem, but Lime has it like in the worst possible state. Next question to ask. So we determined most important features. Now it's time to find what is the dependency between feature and target and prediction according to the model. And again, we're checking if our dependencies seems okay to us. We're checking if dependency does not have these bumps and peaks, because this again is symptoms that you have some problems with your data. And there are several tools to do that. I personally use accumulated local effects in Alibi library, but partial dependency plots are good, is a good choice as well. So I recommend to pay attention to those stuff. And also the library called Interpreted. It's just a brilliant idea. I really like this library. I used it quite a while. So this library cannot make your models interpreted. Instead, it is training fully interpreted, fully white box models from scratch. And the idea is following. So in all models, in machine learning, we're training model, a function f, which takes all input features and try to create this function which predict the target. In additive models, we are doing quite a different stuff. So we create a separate function for each input feature. And these functions f1, f2, fn, they're called shape functions. And then, of course, we just combine the results. So the final prediction is just a combination of all of those shape functions, output of those shape functions. And the huge plus of this approach is that by doing so, of course, we're not taking into account intersections between features, which in some cases is very good for our, very bad for our problem. But by doing so, we actually could inspect each of those shape functions and understand how this particular value of this feature affect the final predictions, like what is contribution of this feature, which is pretty similar to the SHAP, but this is done in very good theoretical manner, let's put this way. And this interpreted library is quite accurate. It's fully white box. You may see a benchmark on several data sets compared to XGBoost random forest, and the results pretty good actually, even taking into account that no intersections between features were taken into account. And the most important part here is that we actually could inspect, again, those shape functions. That's why we started using this library. So right part of the screen, we call our explainable boosting classifier, we train it, we ask it to show most important features. And for example, in this task, we may see dependency between output of the shape function and age. I believe in years. So we may see that between 20 and 70 years, the shape function seems quite nice, and we may understand this dependency. But after 70 years, the shape function is not smooth. It's just jumping up and down. For example, here for 80 years, the output of model would be 0. But if you are 79, it would be something like +1, and if you're 82 or 83, it will be plus 0.5. Of course, it's not desirable. We want our shape functions to be smooth, and it is a sign that probably in the training data we don't have enough training points, and we may correct actually this shape function. So we set this part of shape functions of shape function, and for this part we may just plot a straight line. It's not possible out of the box, unfortunately, but I think you got the idea. So by doing so, we actually improving our model even further. We're not only explaining but even improving our model. So we change this part with a straight line, the part after 70 years, and we may retrain our other shape functions, or we may keep the results as is and push model to the production. The last part, but not least, is to check how we should change the input so it would classify as another class. And the general idea here is to understand. So we train our model, we make predictions for the validation data, and generally it's a good idea to check on what examples model made a mistake and what features contributed to that mistake. I talked about it previously. One way to do it is to use manifold, but other ways to do it is to take each point separately, the points with the highest difference between prediction and the target, and to find the closest point to the given one, but with correctly predicted class, and compare feature values of those points. And it might give you some insights of the separation curve of your model and what you may do in order to improve your model. So this idea, again, I'm using my own custom script for that. I'll explain later why. This idea is presented in the Google's What If tool. So this tool basically do what I described right now. And it may also show you some metrics across different subgroups. It may show you partial dependencies plots for different features, which is also good attributions of this dashboard. But the main problem that this Google's What If tool works only with TensorFlow models. Of course, you have random forest, gradient boosting in TensorFlow. Well, I believe you should have those, but I prefer to use LightGBM, I prefer to use CatBoost, and it's not possible to do that using this tool. Also, you may use variants of counterfactual instances. This is actually a smart idea. So the idea of these counterfactual instances is following. So those methods are only applicable for models to which you may calculate gradient. well, basically it's neural networks. And when you're training neural network, you have fixed input, you have fixed output, and you are updating weights of your neural network in order to minimize the distance between your prediction and your target. When you are explaining your model, on the other hand, you want to reverse this task. So now the model is fixed, and you want to find such input which maximize or minimize the output. And this is a smart idea, no doubts, because neural network, especially if it's a well-trained neural network, if it's model like Oracle model with 100% accuracy, it might find the instances right after this separation curve. The problem is that it is an iterative process, and even after few iterations of this optimization, your points may end up in the spaces where you have no training points at all. So basically, in the space where points are improbable in general. So maybe you want to optimize a credit score, and output of your model could be, well, you have to work 50 days a week or something like that, which is just not possible. But from models output, it is possible. The idea of this SEM alibi, it's like last example on the slide, is that you just you say to the model, well, you may actually optimize, you may update your input, but please be in the specified circle around this point. Again, it is a good idea, but it doesn't work. I tested several times on my own tasks, and I just end up in the situation where the output is far away from the initial input of the model. And this whole idea of working with gradients looks very similar to the adversarial examples. So these counterfactual examples are actually adversarial examples, but for explaining and making these adversarial examples for your input for interpretation. Well, I'm not very fan of this stuff. Yeah, so this is all from my side. Thank you for your time. Thank you for your attention. This is a link for a presentation, and I will be happy to answer your questions.
All right. Thank you so much, Dennis, for the presentation. It was really interesting. And yeah, we have a couple of questions in the chat. And I guess we will start with a very interesting one. It's a kind of philosophical question. So Ari is asking, how do we know that understanding machine learning model in general is possible for humans? What does it even mean?
Well, it's actually a great question. And what I specifically like about all papers related to the interpretability is that very, very good papers start by asking what does it mean to interpret a model to the person. And I don't think it's just a question to which we may find an answer because it's really too complex. And there couldn't be any exact answer. But I don't think you're satisfied with this answer. So personally, I believe that if you may copy the exact steps of the processing as model did, that means you understand how it works. So basically, if I may reconstruct the predictions, that means that I can recreate them. What does it mean? So for example, deep neural network with 100 layers with million of parameters, I cannot calculate all mathematical formulas. I cannot calculate all output of each layer and so on and so forth in limited amount of time. Theoretically, I can do it, but in reality, I cannot. But if I'm using, let's say, logistic regression with 5 input features, I cannot multiply each input feature by its own weight and produce an output. And in this sense, I can understand how this model works. So that's probably my answer to this question.
All right. Okay, so let's move to another question. So Andras is asking, how can we use these techniques for large and high dimensional data?
Good question. When you're working with large data set, generally it's a good idea to take a subset of your data set. For example, you may start by training a small model on a subset of data set, or you may use a subset of data set for explaining your model. How to select the size of this subset? Well, that's pretty straightforward. You need to find a such subset of data set after which output of your interpretation tool does not change. And commonly it might be just 10% of your data. Again, it's task dependent, but it might be really small, workable, the amount of data which fits in RAM memory. If we're talking about working with a lot of features, I think generally it's a good idea to run some sort of feature selection or work only with most important features when you are running interpretation. For example, if your model consists of 10K features, I bet not 10K of them are most important, but only maybe 20, something like that. And you may save a lot of time by working only with those 20 features. But again, it's real task dependent.
All right. Okay. So we have another question from Tommaso. He's asking, he thinks that those interpretability tools are only working for tabular data and where we have clearly defined input features. So what about interpretability for other settings? For example, in the sequence classification problem.
Mm-hmm. Yeah, my presentation was mostly about, it was fully about tabular data, except last part, but anyways. So there are tools which can work with tabular, there are tools which can work with NLP data, with text, with computer vision, with sound, with videos. But personally, I don't work with those types of input data, and that's why I didn't present them in my presentation. But I recommend just to go through most famous tools for interpretation, such as Sharp. You may check Lime, Alibi, and those tools could provide you approaches how to interpret computer vision, like what are most important parts of the picture, text, like what are the most important part of the sentence, and so on and so forth. So it's possible to interpret this non-tabular tabular data set, tabular input data. And there was second part of the question, wasn't it?
Is for example, sequence classification problem. How can we interpret?
Well, it actually depends. It's a hard question. I believe that every input data can be every model, every type of data can be interpreted. If we're talking about sequence data, we probably may use again. It depends on type of the model that you're using. If you are using some sort of gradient boosting machine for classifying your input sequence, or just go point by point, you may use the same tools which I listed here, but I would like to add some constraints. So basically, you cannot change the interpretation like dramatically. So two close points should have same interpretation. If we're talking about sequence classification using deep neural networks, well, there are a lot of works in which authors using attention layers in order to find what part of the input sequence contributed the most towards final prediction, like to which part of the input sequence model paid more attention. So basically, answer here: use attention, use transformer architecture to find those attention maps.
All right. Maybe another question in the same context. So Eva is asking if there is any best tools for explaining NLP predictions.
Again, I'm sorry, I'm not working with NLP a lot. I would recommend still check Sharp. It should work with text, and Alibi. Two libraries, both were mentioned in my presentation.
Yeah, I guess as Mehran Ali is commenting here, he said as long as it's feature importance based on the feature target dependency, I guess we can apply this kind of tools, right?
Yeah, it is actually probably a good question. Can we apply the same strategies for unsupervised models? For example, if you are doing clustering analysis, cluster analysis, can we use the same logic for finding most important features? Well, sometimes it's not useful. For example, in k-means there are no important features, but we may transfer the task of unsupervised learning in supervised approach. So basically, for example, we cluster our data. Why not to feed a model to predict the cluster label? And if the accuracy is high enough, that means that we may inspect this supervised model and find what are the most important features which affected these like different clusters. And also there are a couple libraries which can work with interpretation tools from with unsupervised models. Probably I worked with isolation forest, the tool which allow you to find what are the most important features for isolation forest. Isolation forest is a tool for finding anomalies in your data. And probably that's it. Maybe there are a couple other tools. So, yeah.
All right. Yeah, some people are asking about the slides. Are they available after the event? I guess you have this link here with this QR code. Does it redirect to your GitHub or?
It redirects directly to the presentation. Yeah.
Okay. All right. Cool. And for people who are interested in getting the slides for Oguzhan presentation, please email him at Oguzhan. Well, he mentioned his email in the chat, so feel free to reach out to him for the slides. Okay, let's see if there is any other question. Yeah, we have another one from Vladislav. He's asking, is it possible to automate the interpretation if you are training number of models? In other words, do the explanations require a human to make the decision in hyperparameter optimization or model selection?
Well, there are actually two questions. First one, can we automate model training? And answer is yes. We may use different tools for hyperparameter optimization. Personally, I use Optuna to do hyperparameters because, well, general people cannot work in the high dimensional space of choices for hyperparameters, such as, for example, for light GBM, number of trees, depth of your of tree, and number of lists and stuff like that. Models do it much better. So the answer for the first part of questions, yes, we can automate this, and you should do that if you're not already doing that, because it will improve scores of your model by dramatic margin. If we're talking about interpretation, the things are quite tricky here. Generally, in the industry, for example, if we're looking at automated machine learning tools such as H2O, DataRobot, Google AutoML, what else? Yeah, I think 3 is enough. So these guys, they're actually trying to add sharp importance calculation for the pipeline of making the model. And generally, I don't think it's a good idea. And well, it's a good stuff to have this, but it's not a good stuff to pay attention to why I'm thinking this way. For me, model interpretation is not automatable at all, because it is a work in which you should make hypotheses and test them using several tools. And I don't think that this automation of hypothesis making and testing is incapable of current state of AutoML. Yes, of course, you may calculate sharp importance, but still, it's not answering some of your questions. You may create this partial dependencies plot automatically. Again, this is good stuff. But are you actually understanding why you're using these tools? Like why you're calculating these most important features? Why you're making this partial dependencies plot? Maybe it's not even useful in your task. Maybe you should use another tools. So for me, again, I'm sorry that I'm repeating myself, but for me, interpretation is just making hypotheses about your model and try to check this hypothesis with with the tools which are available to you.
All right. Okay, I guess we don't have any other questions, but I guess I have one quick question. So what is your take on the Bayesian deep learning for interpreting deep learning models? Do you have any thoughts on that?
Wow, it's a hard one. Right at the end of the presentation. To be frank, I'm not very familiar with Bayesian neural networks. A year ago, I took part in the Sberbank AI conference. It's a very famous conference in Russia. And one of the presenter was, I believe his name is Gennady Vetrov. He's extremely famous in scientific circles, extremely famous person who spent a lot of time working with Bayesian neural networks and with neural networks in general. And he presented a comparison of different approaches, how we may calculate uncertainty in deep neural networks. And I didn't understand a single word he said in his slide because it was a pure mathematics, but I understood the following. So I understood the final results. So if you want to calculate uncertainty in deep neural networks, the best idea, the best approach you can take, again, might be just my understanding, because I'm completely wrong here. We just like cut this out during post-processing. So the general idea was that if you want to collect uncertainty, you should train a lot of runs of the same architecture with the same data, but with different choice of random seed, and then just average your predictions and calculate, let's say, average and standard deviation that will give you uncertainty estimation. It is not an answer to your question, but I think it will provide you some understanding of what I'm thinking about interpretation using deep neural networks. So it's a hard topic, and I'd like to see some results which could work out of the box. And some people who are already worked with such models and then apply it in my own work, because I'm not a researcher. Well, I do some research work, but I don't want to spend months of research when I have a lot of projects to be done.
All right. Thank you. Thank you for the answers. Well, I guess we still have one last question from Ali. He is asking, what are your thoughts about simple decision trees or association rules for interpretation?
It is actually a good idea to have a simpler models instead of complex ones, generally speaking. Unfortunately, there are not too many tools which can allow you to do this stuff of interpretation out of the box. But I really like the following framework, which I will describe now. So the idea here is that in our training data, well, commonly training data is large, right? We have thousands of examples in our training data, but very few of them are actually useful. So a lot of examples in the training data are actually just the same examples, but with slightly different features. And we don't need too much training data in order to fit our algorithm, right? So the idea is that we may find the most important training examples in our training data, and then using a smaller version of our initial training data, train a much simpler model. And this approach, it was tested using the SHAP. So in SHAP approach, you calculate the contribution of each feature in the final prediction. But the same approach could be applicable for training data as well. Just calculate contribution of every training instance towards final loss, and select the instances with the highest contribution, and then you train your model on those smaller training data. And the researchers, again, if you want the link to the paper, just DM me in LinkedIn. The researchers found that when we are using smaller training data, but carefully selected and simpler models, we may have, not better model, but quite compatible models compared to these complex ones. And I believe this approach is quite robust. quite good to have in your data science toolbox. Unfortunately, there are no tools which can allow you to do it out of the box, and you need to write this code yourself. And this is greatest limitations of all.
All right, thank you so much. So I think we are at the end of this meetup. Thank you so much, Dennis. It was really interesting and a pleasure to have you.
Yeah, thank you.
Thank you. All right, so thank you everyone for joining the first PyData Helsinki Meetup. It was a pleasure having you all here. Please, we have a quick survey or a couple of questions if you would like to answer about the general feeling about the meetup and some other questions. Please, in the chat, you can find a simple Google form that you can fill quickly in under 1 minute. So please help us get some feedback about this session. And we are really looking forward to have you in next month, hopefully with more speakers. So we are, again, looking for speakers. So if you are interested, please leave us a message or an email at our email, pydatahelsinki@gmail.com, or reach out to one of us, one of the organizers, or you can find the proposal talk form in the Meetup page. So if you go to the Meetup website, meetup.com/PyDataHelsinki, in the group description, you can find the form that where you can submit your proposal talk, and we will be happy to have you here to share your knowledge with us. I think that's it. So it's 7:32. That's okay. And yeah, thank you so much, and see you next month.
Thank you a lot. Bye-bye.
Yeah, bye.
Thanks, bye.
Thank you.